Good morning, everybody. Good afternoon. Sorry. I hope that you're all fine and that you're doing well. Um, I have created this Zoom session because we still have issues with the portal. We are not able to access the big blue button in the Moodle platform. So this is how we are going to do it as we wait for all those issues to be corrected. But I hope that you're all okay. You're all fine. So today's class, computer organization, today's class we are going to discuss more about memories, computer memories, as you have seen, as it is actually there. It's also it is the topic for the Zoom meeting, memory. So we're going to discuss about memories, computer memories. So for today, we are going to look at memory organization, or what we call memory hierarchy. Let me share a screen so that we can begin. The rest that join us, they'll join us as we continue. So memory hierarchy. Now, memory hierarchy is basically deals with the organization of how different kinds of memories, computer memories, are organized and how the CPU is able to access them. So in memory hierarchy, we are going to see the organization of different memories and also how the CPU can access them in terms of speed, how fast or how slow can the CPU access those kinds of memory. So it's a memory organization or a memory hierarchy. So it deals with how memory units are organized in the computer or in the computer system, and also how fast or how slow the CPU is able to access them during processing. Okay. So in the memory hierarchy, this is how the memory hierarchy is normally perceived. It's normally perceived as a pyramid or a triangle. Let's talk about a memory hierarchy pyramid. Yeah. So at the top there is the registers, then followed by the cache memory, followed by the main memory, or what we call the RAM and the ROM, then the magnetic disks, then the magnetic tapes. Okay. Now, while going up, all right, while going upwards, the memories that are on top, all right, the memories that are on top, they are what we call the fast memories. In other words, the CPU can access them fast. All right, the CPU can access them fast. So we can say that actually registers are faster than cache. Cache is faster than the main memory. The main memory is faster than magnetic disks, and magnetic disk is faster than magnetic tapes. So also as you go up the pyramid, the literal cost, the cost for these memories increase. Okay, the cost for these memories increase. That's why you normally realize that if its main memory, if a computer has 2 GB or 4 GB of RAM, and then you increase, you have another computer of the same specifications, but it has 8 GB of RAM, then you realize it's way too expensive. Okay, so basically, as you go up this pyramid, the cost increases, the cost of the memory increases, and also the speed of the computer increases. Why? Because the CPU is able to access memory faster. All right. So if the computer has more registers, then it becomes faster because registers are high-speed memories. Okay. It is easier to access data or instructions from a register than it is from a cache or than it is from a main memory going down that way. Okay, so what we have here, what we call the increasing order of access time ratio. Access time ratio is basically the speed of accessing what? The speed of accessing that memory, or the speed of accessing instructions in that memory is called the access time ratio. Okay, so this is the memory hierarchy. This is the order. At the top we have registers, then cache memory, then main memory, then magnetic disks and magnetic tapes. All right. So the ones that are further below in the pyramid are slower kind of memories, and they're also cheaper. All right. But the ones that are further up the hierarchy are faster and are also more costly. Okay. Now let's discuss this memory hierarchy. Now let's now discuss this memory hierarchy. Now let's begin with registers, which are at the very top. Njuguna Kelvin, are you able to hear me? Or everyone else? Are you able to hear me? Njuguna Kelvin says that he's not able to hear. Is everybody else able to hear what's going on?
Yes, can hear.
Okay, then.
Yes, can hear.
All right, let me continue then. So the memory hierarchy, let's start with registers, which are the very top of the pyramid. And what they do. So let's see what they are. All right. So registers, they are usually, a register is a static RAM, or what you call an SRAM. And it is used for holding the data word, which is typically 64, 128 bits. Now, what makes the register very important to the CPU? The register is important to the CPU because of this. Most of the processors uses a state word register as well as an accumulator. A status word register is used for decision making, and the accumulator is used to store the data like mathematical operations. Now, registers are very important to the CPU since because of the first one is the amount of data they can hold per unit time, 64 to 128 bits, as opposed to the RAM and others, which can vary. All right, can vary and is lower. And also the other importance of the registers to the CPU is that the registers also holds instructions that the CPU uses for decision making. The registers hold instructions that the CPU uses for decision making. Also, the registers holds instructions that are related to mathematical operations. So those are the three reasons why the registers are very important to the CPU and why they are they are atop the pyramid, the memory hierarchy pyramid. Number one is because of the amount of data bits they can hold per unit time, 64 to 128 bits. Also, they can hold instructions that the processor uses for decision making, and all these instructions are very many. So the CPU always keeps doing all these instructions can vary from mathematical operations and logical operations. Logical operations are what we call decision making operations, and normally performed by the arithmetic and logic unit. So for those instructions, before they are loaded to the arithmetic and logic units, they are held by the registers. Okay. So, and also mathematical operations, they are computed by the arithmetic and logic unit. Please, Njuguna, please correct your correct your audio, because I think it's only you that cannot hear. All right, so that is why the registers are very, very important, okay, to the CPU, because they hold for the CPU instructions used for decision making, instructions related to mathematical operations, and they are also able to hold 64 to 128 bits. Normally when you are buying a computer or a machine, you normally hear it is that computer is 32-bit or 64-bit. Basically 32-bit or 64-bit is basically the description of it's normally a description of the amount of bits that the CPU that can be transferred to the CPU per unit time by the data buses from the registers. Okay, so do you remember the data buses? Data bus, address bus, and the buses, data bus, address bus, and control bus. So data buses are used to do what? To transfer data from the memories to the CPU. Okay, so what happens is that when you say a computer is 32-bit or a 64-bit, what you're basically saying is that that computer, if it's a 32-bit, it can transfer 32 bits per microsecond to the computer, to the CPU per microsecond, if microsecond is the unit time. Of course, more modern computers are using nanoseconds, but of course we're using micro for most of the computers that are existing. So when you say a computer is 32-bit, you're basically saying that there is a transfer rate of 32-bit per microsecond through the data buses from the registers to the CPU. All right. When you say a computer is 64-bit, basically you are just saying that, okay, and it keeps multiplying. All right. So that's why the registers are very important, because they can hold 64 to 128 bits. All right. When we go down further the hierarchy, we find the cache memory. So by virtue of cache memory being number 2 and registers being number 1, we can basically conclude that cache memories, the CPU accesses the cache memory slower than it accesses the registers, because it is going down the memory. Okay. Now, what can we say? A cache memory is basically it is a kind of a memory that holds the data which are frequently used from the main memory. When the processor has a single core, we talk about core i3, core i2, core i5, all right? When the processor has a single core, a core is basically a logical unit of a CPU, okay? A logical unit. One processor, but it has logical units, right? Logical units, and each unit functions like its own processor. So when you talk about core i3, you're just talking about a computer that was one CPU that has 3 logical units of the CPU, and each of those 3 units each of them works as though it is a CPU by its own. Therefore, what does that do? It helps to facilitate and make better the multiprocessing environment. So the CPU is 1, but it functions like 3 because it has 3 units called cores. Okay. So when the processor has a single core, then it will have 2 or more cache levels, sometimes. But multi-core processors will have 3, some will even have more. Okay. So basically, a cache memory is a memory that works as it works like a backup for the main memory, and the main memory here is the RAM. Okay, it works as a backup for the main memory. All right, and it works the same way as the main memory. Its functions are the same as the main memory. What are the functions of the main memory? To hold data temporarily before instructions, or to hold instructions temporarily before execution by the CPU, and also to hold instructions temporarily after execution by the CPU. So the cache memory works the same way like the RAM. The only difference is that it is faster. The CPU can access the cache memory faster. So if the computer is loading a program that has many program threads, a program that has many program threads, basically a program that occupies a large storage capacity. For instance, if you are opening a game like Euro Truck Simulator or FIFA, yeah, or you're opening this kind of applications that are memory intensive, these program threads will be intershared, will be loaded to the RAM, but the processor will be accessing them from the cache and the RAM. So some program threads will be temporarily held by the cache, and some program threads temporarily held by the RAM when that program is running. So the CPU accesses it from the cache and the RAM alternatively, but it accesses from the cache faster than it accesses from the RAM. All right. So that is why we are saying when we are dealing with programs that are memory intensive, then the cache memory comes in handy. It comes in handy because it is faster than the RAM, but still does the same function as the RAM, which is to hold program threads when an application is running. Are you together? Yeah, and especially for very big program threads, the cache memory will be very important with that, okay? So that's the function of the cache memory. Then the main memory, here we are talking about the RAM and the ROM, okay? Now we can say here, because they are number 3 by default, they are slower. The main memory unit is slower than the cache and slower than the registers. Okay, you see, as we are going down the hierarchy, the speed of the CPU accessing those memories goes down and down and down. Okay, so the main memory unit is slower, and it is composed of the RAM and the RAM. Now the RAM is the functional main memory. It is the most active main memory. The ROM can be in form of the CMOS, the complementary metal oxide semiconductor, or which hosts the BIOS and the date and time, system date and time. All right. And also the firmware, which contains the manufacturer details. Those are particular types of ROMs that are normally in the computer, but they are not very active. All right. They are not very active. Apart from, of course, which one? The system date and time. That particular read-only memory in the CMOS is what? Is active, because it is what the CPU uses to allocate what? Time to each of the applications that are running. But basically what I'm saying is the RAM is the most active when applications are running, because that is where all applications will be loaded. When you open any application, all the program threads, I think you did operating systems at some introductory levels, and you are told that one of the functions of the operating system is to do what? Is to do what we call processor scheduling. Okay. So in processor scheduling, one of the activities in processor scheduling is to basically arrange all the applications or threads that have to be executed by the CPU in a certain order in the active memory. And the active memory here is the what? The RAM. Okay, in the active memory, so that the CPU can be fetching them for processing, okay, using certain algorithms like last in, first in, first out, round robin algorithm. All right, those kinds of things. So the main memory is basically for holding what? Applications that are to be run by the CPU, to be executed, and also the results of instructions being executed are also loaded back to the RAM, and then they can go to output devices. You can now see whatever you are typing, you can now see it on the monitor, or if it is music you are playing, you can now hear it through the speakers. Okay, if it is a document you are printing, you can now see it being printed by the printer, yeah, or even taken to the storage like the hard disk. Okay, so the RAM is basically the active memory that holds data and instructions before and after processing. Okay, then magnetic disks, these are basically circular plates, right, that are normally magnetized. They store their data in magnetic form, and basically magnetic disks have one example of a magnetic disk is what we call the hard disk. Okay, the hard disk. Now, the hard disk, this is how it functions. The hard disk normally has a read and a write head. A read head is basically a spindle, or we can say it's an arm, like an arm, the arm of a person. It's like an arm, a metallic arm that has a magnetic edge. And basically, the work of that read head is to read or access items from the hard disk when the user is, for instance, opening a file. So when you open a file that is in the hard disk, for instance, when you go to your hard disk and you click open on a certain document or a certain file, it is the work of the read head to access where, a hard disk is normally divided into what? Each disk is normally divided into sectors, right? Remember introduction to ICT. So a hard disk is normally the disk, every disk, because there are different, every disk, every has to mic. Ensure that you mute your mic. So as I was saying, every disk is arranged around a spindle or around an axis. Okay, every disk is arranged around a spindle or around an axis, and then the read head, when you open a file, the read head reads. Okay, just as the word suggests, it reads the sectors, because every disk has what? Sectors. It reads the sectors to find out where that particular document is, and then when it finds it, it now opens it and you can see it on the screen. Or if you are playing a game, it is the read head that keeps reading every part of that application as you are gaming, okay? Or you are watching a video, it is the read head that keeps reading that video until the end. All right. Then what is the right disk? It is exactly the opposite of the right head. It's the exact opposite of the read head. Right head, basically just like an arm, it has a magnetic edge, and basically its work is to write into the empty sectors of the hard disk. For instance, when you are copying a file to the hard disk, it is the right head that writes that information or that file or that folder, whatever you're copying, it writes it into the hard disk. Okay. Then if you are writing a document, all right, you have a document that you've saved, but you are editing, you are making some changes. Okay, you are making some changes, you are adding things in here and there. So when you save that file, it is a right head that writes those changes into that particular sector where that particular file is. Okay, so that's how magnetic disks work. They function magnetically. They write and read data using magnetic technology, but they are slow. Okay, they are slow compared to the RAM, compared to the cache, and compared to the registers. That is why you always find out that the operating system is in the hard disk. Yeah. So when the complementary metal oxide semiconductor, it has the BIOS software, right? The BIOS software that is responsible for booting. All right. So when booting successfully completes, it hands over control to what? The operating system. All right. But then you realize that that process is normally a little bit slow. After booting completes and then it gives over control to the operating system, you normally see in your screen there is something going around. It is making a circle. When it's going around, it is loading the operating system. What is happening during that time is that the read head of the hard disk is reading the utilities, or what the operating system where it is in the hard disk. Then it discovers it, then it opens it, then now you're able to sign in into your account. The operating system has now been found. Okay, so basically that's why we are saying it is slow, because every time booting completes successfully, there is that a small period where you'll have to wait for the OS to be loaded. Okay, so that's why magnetic disks are a little bit slow, but they use magnetic technology. Okay, they use magnetic technology. Right, so we have discussed that. So remember those things that we are mentioning: sectors, write heads, read heads, and such things. Then magnetic tapes. Were you born during magnetic tapes? Do you remember cassettes? Cassettes are what we call magnetic tapes. Now, basically, a magnetic tape is normally it's just a very slim magnetizable film, which is normally a plastic film, okay? And it is magnetizable, meaning that it can store data in it in magnetic form. Okay, and it is mainly used to back up huge data. So magnetic tapes are what we would call cassettes or video tapes. You remember the VCRs, the video recorders, the VCRs, the ones which you would put a tape, a very big tape in there, yeah, for video. So those are magnetic tapes, okay? And they are slow. How do they store data? Inside a what? On top. It's normally not inside, it's just on top of that surface, on top of a magnetized plastic film, okay, on top of a magnetized plastic film. All right, magnetized plastic film. All right, we are having less than 10 minutes so that this session can close. I create another one. Let's look at memory hierarchy concepts. Some concepts associated to this hierarchy that we've just discussed. Let's look at these concepts. The first one is performance. Right now, performance, when designing of a computer system, uh, the the performance is basically it's basically the speed of the processor, the speed of the processor accessing that particular memory. That is performance. And how do we measure performance? In this hierarchy, performance, the higher you go up the pyramid, the greater the performance, okay? The speed, all right? So that's it about performance. What is the ability? It is the total amount of data. This is another term used in relation to memory hierarchy. Right? Ability is the total amount of data the memory can store. Okay, so look at this. As you go down, now this is different. As you go down the memory, as you go down, the more the amount of data can be stored as you go down. All right, because consider something like, you cannot have a register that stores 500 GB. You can't. Registers normally just store a few MBs, okay, a few MBs. The only thing that makes registers efficient is that they are fast. The people can access from them fast. That's it. It can empty load at a very fast interval, okay, which the hard disk cannot. And the hard disk belongs to which disk? Magnetic. All right. The hard disk is big. It can even have 1 terabyte, but the storing and storing, it is a slow process. All right. So the ability increases downwards, performance increases upwards, okay, because of the speed of access. But ability, which is the amount of storage per memory, increases downwards. So that the downer you go, as you go downwards the hierarchy, the ability of the memories increase, the amount of, because let's assume we are dealing with RAMs. You will never find a computer that has more than 32 or 64 GB memory, but you can have a flash disk that has more, 128 GB. It has even more, even a hard disk. You can have a hard disk that has 1 terabyte, 2 terabytes. All right, you can never find a RAM that is 2 terabytes. It is not there. Okay, it's not there. So basically, not unless you are dealing with supercomputers and you are basically using different RAMs. You cannot have one RAM that is 1 terabyte. Okay, because they are not designed to hold a lot of data. They are designed to hold just a minimum amount of data, but have a fast access time. Okay, so the ability increases down the hierarchy, the performance increases up. All right. And then the next thing is access time. Access time is the amount of time required to access the instructions or data in a memory unit. The access time in the memory hierarchy is the interval of time among the data availability as well as request to read or write. All right. Do you understand this statement? It is the interval of the time between data availability and request to read or write. For instance, if the CPU is loading the OS, the CPU is loading the operating system, there is that interval between the OS being found, all right, and then the OS being the sector being found, and the read head reading that OS from that sector. That particular period of time is called the access time. So the access time is the amount of time required between when that file or that particular program is needed to the time it is read, or when that particular file, when a particular sector has been found, if it is a hard disk, to the time writing will begin if it is copying a file. Okay, so the interval between data availability and the read or write, it's normally called the access time. And generally, we are saying that the access time is the amount of time it takes for the CPU to read or write into, to read from or write into a memory unit. Okay, that is access time. What is cost per bit? Cost per bit is the amount of it is the cost, basically the literal cost, the economical cost, the economical cost for storing or handling every bit of data, the economic cost for storing or handling every bit of data. And we are saying that this cost will increase down the up the memory, not up the hierarchy, not down, which means an internal memory is expensive compared with an external memory. So if you look at this hierarchy, a RAM is expensive to a what? A magnetic tape. True, because look at it. When you buy, if a computer is 25,000 shillings, let's say an HP computer, HP computer Windows, which has it has an operating system. It is a Core i5, or let's say a Core i3, 500 GB hard disk and 4 GB RAM, and it's 25,000 shillings. If you have another computer of the same specifications, but you have 8 GB RAM, suddenly the cost will shoot from 25,000 to 32,000 shillings, or even 35. Okay, what has made that difference? It's just RAM. The other specifications have remained constant. You've just added 4 GB RAM, and the cost has increased to how much? Has increased by 25 to 35. That's 10,000 shillings. So adding 4 GB RAM, you've added 10,000 shillings. Just that. That's why we are saying that the cost per bit increases up the hierarchy, because down the hierarchy, the cost per bit decreases. All right, because let's talk about let's talk about things like flash disks. All right, flash disk will fall under of course we know flash disks are not magnetic disks, okay, but under these, in these two, we can treat all of them as auxiliary memory. Auxiliary memory are, external memories. They are called auxiliary memory, external. They are not inside the computer, they are outside, okay? Apart from the hard disk, of course, which is inside the computer. So let's deal with auxiliary memory, which are at this level. And we talk about the flash disk. The flash disk can be 4 GB, you can get it at 400 shillings. If it is 8 GB, you get it at 600 shillings, all right? So 4 to 8, you've only added 200 shillings, okay? Or even 300 or 400 maximum if you're getting a good seller. So let's say maximum, you've just added 400 shillings for a 4 GB increase. But if you add 4 GB RAM to 8 GB RAM, you've added 10,000 shillings. So can you see what that does? So the cost per bit is lower when you are dealing with auxiliary memories, but higher when you are dealing with the other memories on top of the hierarchy, the main memory, the cache, and the registers. And why so? Because you have, when you add the memory, you've added, I can see our time is lapsing, but when you've added the memory, you've added for yourself two benefits. Number one, cost, access time, and number two, performance. All right. So that's why it becomes very expensive. All right. So I think I need to create another session because this one is elapsing. So let me create another session.